My name's Jared Heitzler. I am the Foundations Manager at Martin Engineering. Today, we're going to talk about engineered controls to reduce conveyor dust. About a month ago, I delivered this presentation at the National Stone, Sand, and Gravel Association's annual conference in St. Louis. And the reason why this is such an important topic, if you're in the US and you're in the mining industry, you may have heard of the new silica dust standard that MSHA is going to start enforcing about a year from this week. If you're a coal mining facility, that's already been implemented and they're enforcing it now. So what's going on with MSHA right now is that they're trying to reduce the cases of black lung, trying to reduce the harm and increase the health on miners. And silica dust is a proven carcinogen that damages workers' lungs when they're exposed to it. So MSHA, along with some research that was provided to them over the course of the last 7 or 8 years from NIOSH, has given some instruction and some direction, and soon to be giving some enforcement on this new regulation to combat or control silica dust. Now, the concepts that we're going to talk about today are certainly applicable to silica dust, but they're applicable to any type of dust. So if you're in a residential neighborhood, or if you've got neighbors, or you just want to make for a better environment and keep material on the belt rather than sending it airborne, the concepts that we're going to talk about today and the concepts that I talked about at the National Stone, Sand, and Gravel Conference are going to be applicable. There's really two types of, there's two efforts or two schools of thought that you can use to control conveyor dust. What we're going to talk about today is what we call passive dust control. Passive dust control can be defined as methods to control dust without capturing that dust or suppressing that dust. What passive dust control is, it's really manipulating the air speeds that carry dust. See, we believe that dust isn't as problematic as what you might see. The dust itself is cargo, it's material that you're either selling or either that you've bought, that you're moving, that you want to get from point A to point B, and you want it handled properly. The only time that dust becomes, or that cargo becomes problematic, is when it's exposed to air speeds that are fast enough to move it out of the intended place that it's supposed to go. So what we're going to talk about today is manipulating those air speeds. Now, as opposed to passive dust control is what we call active dust control. That's what you see on the right. Active dust control is very, very common, and it's usually the first type of dust control that facilities look at. Active dust control is adding additional equipment to capture or suppress dust without any regard for controlling or manipulating or slowing that airspeed. Usually, active dust control is expensive. It requires a lot of auxiliary equipment, and it can create some unintended consequences that you may not have expected. So we're going to talk a little bit more about that. So there's some real benefits of passive dust control. Passive dust control it doesn't require the use of water or electricity as does active dust control. So if you're using some sort of active dust control, you're typically going to use some sort of dust collection system that's going to probably rely on some sort of electricity to operate it. And that vacuums the dust out, and that added electricity comes with a cost. If you're using some sort of suppression system to control dust, another active method, that's going to rely on water, maybe water that's treated with a surfactant or a chemical to make that water more effective in controlling that dust. There's a big problem with adding water to some operations. The biggest problem that we see with adding water to your material to control the dust is that if you're in an aggregate or a mining facility and you're screening materials, that material with that added moisture can stick to screens and blind screens off. It also is going to make the belt much more challenging to keep material from sticking to the belt on its return path. So if you do choose to use some sort of spray system to combat your dust, understand that there may be some unintended consequences, especially by adding water, in that you're going to probably need to increase your belt cleaning efforts. Another benefit of passive dust control is that it really enhances active efforts. So let's say you're a facility who just has to, for whatever reason, maybe it's permitting, or maybe because you just need that added control of dust, you have to use some sort of active effort. Those active efforts often can be ineffective unless you do something in addition to that in slowing that airspeed down. Now, there's lots of companies out there that will promote either dust collection system or dust suppression systems. And in fact, Martin Engineering will promote those as well at times. However, there's nobody that probably should dismiss the effectiveness of manipulating those airspeeds in advance of those collection or suppression systems. The other and the biggest benefit of a passive dust collection system is that it's just simply less expensive. It's mechanical solutions. It's easy to do. It doesn't take specialized maintenance. It's steel, rubber, grinders, and welders, and then those people that kind of know how to use those equipments, those pieces of equipment to kind of make sure that they're doing their job. So what passive dust control system, it's pretty simple. Let me just kind of draw this out for you. If this is our tail pulley and this conveyor belt's running to the right of our screen, and this material comes through a loading chute like this, and let's try to make it three-dimensional for you. So here's my tail pulley. Material, and in this case, our material is red, and it travels through as you see here. And the intent of a passive dust collection is that from point A to point B, no material can escape this enclosure. And the airspeed inside this enclosure must be less than 200 feet per minute before that air gets to point B. If you can slow that airspeed to under 200 feet per minute before it exits the enclosure, typically that dust will fall out of suspension and then not be problematic for you. Now, this works for one belt dumping onto another belt, or maybe a hopper dumping onto another hopper. The key is that it's enclosed, no air can escape until that air gets to point B. And at point B, we slow the airspeed to under 200 feet per minute. So that's just kind of the basics of passive dust collection system. Let's talk a little bit more about those engineered controls to really make it effective. There's three of them, and we're going to talk about each one of them. But those three types of engineered controls to reduce conveyor dust are: number one, got to reduce the air that enters into that enclosure. The second, we've got to use engineered controls at the enclosure. So we're going to talk specifically about the hardware pieces that make up that enclosure. And then third, and finally, we're going to talk about how to really slow that air to under 200 feet per minute before it exits that enclosure. So the first one we talked about was reducing the air in that enclosure. So one of the things about this passive system, as air enters this enclosure, whatever air enters the enclosure, that same volume or amount of air must exit that enclosure. So the more air that you put into that enclosure, the more air that you're going to have to deal with inside of that enclosure. So it's really important that you could really help yourselves out dramatically if you reduce the air that's actually entering that enclosure. There's a couple of ways that you can do it. And what you see here are on those pictures of facilities that have reduced the air entering their enclosure. The picture on the left is just simply some probably like 3-inch minus material entering this head chute. And as that material enters the head chute, they have used some, looks like some canvas in this situation, just to kind of block off that airflow that accompanies that material. In the picture on the right, they've done the same thing. You can see on the top side of the belt, the material enters the head box or the enclosure to the right, and they've added some rubber curtains to lessen the amount of air that accompanies that material flow. But in this case, as the belt exits the enclosure or comes off this head pulley that's inside the enclosure, you can see this belt down here. Air can also be induced from this space as well. So what they've done here is they've blocked off the ability for the air to enter the enclosure in that space as well. So great efforts here on reducing the amount of air entering the enclosure. You also want to try to, if you can, reduce what's or limit what we call induced air. As material comes off a head pulley, that material expands, and as that material expands, it has to surround itself with a volume of air. It's not in a vacuum, so it pulls air in between the particles. As the belt then lands, as that material and air then land on a receiving belt, that material settles and it pushes that air out. That's called induced air, and it's problematic. So what you can do is you can limit that induced air by trying to retain the material path as much as possible and limit that vacuum effect that the material has as its trajectory off the head pulley pulls that air in. So what you see in these photos on the left-hand side, you have kind of a slanted or almost a spoon style approach to the receiving belt. That's going to keep that material tight in a profile and reduce that induced air. In the photograph on the right, you can see they've installed a hood. So as that material comes off this head pulley, it's not allowed, its trajectory is controlled, and the controlling of that trajectory limits the spreading of material, and that limits that material's ability to pull air in. So induced air can also be problematic. You need to kind of take attention to that as well. So that's our first engineered control to reduce dust at conveyors. The second, we're going to talk about those specific engineered controls at the enclosure, or the equipment needs at a transfer point or load zone to really make up the system that's going to keep that air contained all the way to point B. So the intent of this number 2 is to have this auxiliary conveyor equipment installed, maintained, and used to not allow any air to escape this process. It might need to go on for many, many feet, like you see in this photo. In this example, these engineered controls are used for about 40 foot of belt length. In some cases, it might be 20 foot. In some cases, it might be 8 foot. It kind of depends on how much material you're pushing through there, what the speeds of the belt are, what the drop zone is from the giving belt to the receiving belt. But the intent here is that we've got to use these engineered controls all the way to point B. In this photo, point B is way off to the right. So you can see this is an extreme example. You may not have something quite so significant, but it may be. So let's talk about each one of these kind of individually. None of these are really extreme stuff. You've probably seen heard of all this stuff before. Nothing new here for an experienced project engineer or uh, operations or maintenance personnel that might be joining us today. But what I hope to do is give you a little more insight on why these are so important. Let's talk first about belt support. Belt support is it's a critical piece. It's to this system of containing this air all the way to point B. And it's often overlooked or underappreciated. In this photograph, you can see these idlers that are supporting the belt in this load zone look to be spaced maybe, I don't know what the spacing is here, but I might guess it's maybe 20 inches from roller to roller. Okay, that 20-inch spacing in between these rollers can cause that belt to sag in between those rollers. Now, as that belt sags, maintenance crews are typically going to try to reduce the gap between their skirting and the belt by driving that skirting down. Now, that can cause you some belt tracking problems. It will also cause your skirting to need to be replaced too early. Rather than driving that skirting down, the better solution is to make sure we elevate that belt up and keep a stable, flat belt surface for the entire length of that skirted area. So if we go back to this picture, you can see here they've installed a cradle and then idlers for this entire length of the skirted area. Now, these idlers, it's hard to see in this picture, but they look to be maybe spaced maybe 12 inches apart. In some instances, idler spacing of 12 inches apart might be satisfactory. In some instances, you might need idlers stacked right next to each other as close as you could get them. In some instances, you might need cradles to completely eliminate the idlers. Every situation is going to be a little bit different, and it really takes a trained expert to really be able to give the guidance on how you might need to support that belt. One thing that I often see facilities do to try to eliminate that sag is to put excess stretch on the belt. They think if they pull that belt tighter, it won't sag from idler to idler. That's problematic. You don't want to do that. You want to have the correct tension on the belt and not overstretch it. If you overstretch the belt over time, that belt will start to cup. It's one of the main reasons that you'll see belts cupping as they're being operated. When a belt cups, it makes it very challenging to clean the belt properly with belt scrapers, and it makes it very difficult to keep it tracking properly. So if you're seeing belt tracking problems, it might be because your belt's cupped. If your belt's cupped, chances are it's probably over-tensioned. Now, we're happy to help provide that guidance. If you need help with that, reach out to our email address, send us a note, and depending on where you're at in the world, maybe we can send somebody out there to take a look. But if we don't have somebody available or in your area, we're certainly willing to take a look at some photos and consult you through that process to make sure that you don't overspend on belt support, but that you do eliminate that sag. Let's talk about wear liners. Now, this is kind of new. I want to share this with you. If you've joined us before, or if you've gone through our classes, or read our books, or been on our Learning Center, or watched our old webinars, you've heard us talk for many years about an abrasive resistant steel wear liner used to hold back material to let your skirting really be used to hold back the air. So in the photograph on the left, this is what you're seeing. This orange piece of steel, that's an abrasive resistant steel installed to hold back the pressure of the material. Now, the intent of this wear liner is to allow your skirting, which you see right here in the black, to do what it's intended to do, which is to hold back the air pressure. That rubber skirting will not hold back material. That's not what it's designed to do. There's not a skirting in the world strong enough to do that. Its job is to seal the gap between the enclosure and the belt. When that rubber skirting is exposed to material, it's overcome with pressure and it can't hold it back. So the idea of a wear liner is really important. The problem with a wear liner is that if that belt were to touch that wear liner because that wear liner's too close, then you're going to damage your belt. And you'll see grooves in the belt where that belt might have bumped into that abrasive resistant steel. So most facilities are a bit hesitant to put that wear liner close enough to the belt where it's actually effective. That wear liner needs to be very, very, very close to the belt in order for it to be effective. And a lot of people are understandably hesitant to do that. So what we've introduced now is a urethane slab that we're using as our wear liner, and that's what you see in the photograph on the right. You see that 35 written on the side of that? Different conveyors have different trough angles. And that trough angle is usually in the US going to be 20, 35, or 45. So what we're doing is we're putting a bevel on our urethane wear liners like you see right here. Tough to see that edge, but that bevel right there matches the trough angle of the belt. And the intent of that is to get a fantastic seal against the belt. Now, if you look at the gapping between the steel wear liner on the left-hand side of the picture, this gap right here looks to be maybe a quarter of an inch, maybe an eighth of an inch. But here, I just got these pictures from my associates in Mexico. In this photo, I think it was a quarry, a hard rock quarry in Mexico, and they put this urethane wear liner in and are able to set it right on the surface of the belt to really get that minimal gap to really seal material in very well. Because that urethane won't damage the belt, they can get that urethane right on the surface of the belt. And because of that bevel that we have on that slab of urethane, it's going to seal incredibly. So if you haven't seen this, if you haven't used this urethane canoe liner, wear liner, internals, wear liner, however you want to call it, shoot us a note. We'll be glad to send you more information on it. It's fantastic. Doing a great job of sealing material and letting that skirting do its job of sealing air. I wanted to show you this real quick here. This is the before picture to this photo, which is the after picture. It's just the opposite side. But prior to this, they were using these tiles, and what was happening, as it's pretty common, is as you get gaps in those tiles, a piece of material, like you see right here, would wedge itself into this point right here, along with the belt travel, and then groove the belt, causing that belt to need to be replaced unexpectedly and prematurely. So, with these urethane wear liners, you've really avoided that problem of having those gaps, as you can see on the right hand side. So make sure you take that into consideration as well. So let's talk a little bit about skirting. Skirting is pretty simple. We've talked about it a lot already, and it's just simply making sure that you have it installed. And that's what you see in this photograph here. It's installed. It's sealing against the surface of the belt. This wear liner that you see right here is allowing the skirting to do its job of holding back the air. So those three steps are really the sides of the conveyor belt. The tail is a little bit different story. If you try to seal a conveyor belt on the back side, or try to seal a load zone or transfer point on the back side, it's really challenging if you try to seal it right here, because right here the belt is troughed. So what we're recommending is that you build a tail box like you see here, that's built back maybe a foot, maybe 2 foot to the tail pulley. And that tail pulley presents the belt at a flat surface, and it's much easier to seal that belt, seal the air inside this box at that flat tail pulley rather than at the trough. So what we do is we just simply put a little piece of rubber right there, clamp it to the outside. Sometimes some of our guys will clamp it to the inside and then let that little piece of rubber flap down onto the belt. It's going to seal that airspeed that air much better at that backside. So those are the engineered controls that go along with the enclosure. That's how you build that closure to really keep that air contained inside all the way from point A to point B. Before we finish here, I do want to talk about the slowing that airspeed. That's that third engineered control that we use to make sure we execute a proper transfer point. So there's 3 ways that you can slow this exiting air. If you can use one of these, you're going to make a big impact. But what's really incredible is when you use maybe 2 of these or even 3 of these. If you use a combination of these techniques to slow that airspeed, it's greater than the sum of its parts. So if you can use a dust bag along with dust curtains, you'll really improve on your air velocities and knock that dust down. So we're going to talk about each one of these separately, but we're also going to talk about them all 3 maybe used together. So dust curtains, pretty simple strategy here. You've seen this before. If you ever tried to combat dust, this is probably one of the first techniques that people will do to kind of reduce the airspeed coming out of a transfer point. What happens is air exits this enclosure. That air accompanies the material, and the intent of a dust curtain is just to simply try to blockade the air as it exits that enclosure. So it's pretty crude, it's pretty simple, but it's also pretty effective, and that's why a lot of people use it. The photograph on your right shows you a little bit different arrangement of dust curtains, and the intent on the photograph on the right is to not necessarily just blockade the air from exiting, but to force that air to turn through as it passes through these staggered curtains. As that air has to be forced into a different direction, that air will slow, and that can cause that material that's suspended in that airflow to settle. So there's different types of curtain arrangements. We're doing a lot of studying on different types of curtain arrangements, and we're finding some differences on some of these things. So, depending on your application, we might choose one over the other. And what you're seeing here, gang, is what we're doing by peaking the top. We've given an enlarged chute. By adding now, what in this application, we could have put a top right across here, flat. Material would build up, and the air that exits this enclosure would race out of there at speeds well greater than 200 feet per minute. But by increasing the elevation of the sidewalls and peaking the top, we've increased the space that's available for that air to travel through. If we increase that available space, the air that does travel through it will travel through at a slower speed, causing dust to fall out of suspension. And that's what you see in this picture. So this is an extreme angle. I wouldn't recommend loading a belt like this, but this belt loads at that extreme angle. It settles right here. As that material settles, air's pushed out of that cargo, and then it's going to start escaping until it gets to point B. So we got to slow it down. So what they've done in this example is they've stacked extensions on the chute wall as well as peaked the tops to slow that air coming through, give that air more space. As it expands into that space, the air slows, the dust falls out of suspension. So that's the intent of a peaked top. Now, some applications you can't use that. If we go back to our first picture right here, we couldn't use a peaked top in this situation because of this pipe right here. So every application is going to be a little bit different. That's why you got to have these three different techniques: curtains, chute enlargement, and then finally, let's talk a little bit about dust bags. So dust bags kind of do the same thing as chute enlargement, but it localizes that space available for the air to accommodate. So what they've done here is materials loaded onto the belt. The chute height is what it is. They didn't change the chute height, but they did cut an opening on the top of that lid, covered that opening with this vented bag, and used a curtain that you cannot see, but right here, there's a slit curtain. So what happens is air's traveling through here. As that air hits that curtain, it's forced up into that bag. That bag is specifically designed to let some, not all, but some of that air will escape that bag without letting the dust escape along with it. So, gang, that's kind of the gist of what we're talking about here. We shared this, as I mentioned earlier. We shared this with the National Stand Zone and Aggregate Association in St. Louis, and it's gonna be high priority for you. If you haven't already tried to start combating dust, and I expect many of you have, you're gonna have to, because OSHA's got this law already on the books. MSHA's got it as well. It's gonna be enforced. They're training inspectors now on how to test and sample air and things like that. So it's really recommended that you get ahead of this dust, and we can help with this. I don't want you to think that it's critical that you guys are left on your own to kind of implement some of these solutions. Depending on where you're at, I probably have resources available to you that I could get out to you and make sure that they help you out with this. So let's review real quick. There's passive, there's active. Passive systems, they're less expensive. They don't require water. They don't require electricity. It's steel, rubber, grinding, and welding. No specialized maintenance, no additional cost. Reduce air entering. If you can give yourselves a fighting chance of reducing the air that exits that enclosure by reducing the air that enters the enclosure, you're going to be in a good spot. So reduce the air that enters that enclosure. Number 3, you want to make sure you use that systems approach. Proper belt support, wear liner, close to the belt, urethane if you can, and then a skirting system to really seal that air inside that enclosure, and then finally slow that air as it exits. If you have questions, let us know. You can reach either Andrea or I at the email address below, foundations@martin-eng.com, or hop on our website at martin-eng.com.